Dear students, I welcome you for the today's lecture related to the root locus diagram in the process control. This is basically to understand the stability of a control system. We have already discussed the Routh-Hurwitz stability criteria for understanding the stability of control systems. Now, root locus diagram is a second method which gives the detailing of the stability analysis of the control systems. So there are certain limitations for this Routh criteria and there are certain advantages for this root locus. So this root Routh criteria, it is simply an algebraic method and that can be used for polymeric equations only. It determines whether the system is stable or it is unstable. It does not indicate the degree of stability. Now, yesterday we have seen this figure, that is an imaginary axis and real axis. If the roots lies on the left hand side of the imaginary axis, that is the roots are negative, then the system is said to be a stable system. And if the roots of the characteristic equation they lie on the right hand side of the imaginary axis, the system becomes unstable. And if they lie on the imaginary axis, then the system becomes just unstable. This much only criteria or this much only is the information that is available from this Routh criteria. It does not indicate the degree of stability, कितना देर वो stable रहेगा और किस values के लिए वो stable रहेगा. That is not indicated by this Routh criteria. It does not give the information on the overshoot. That means how much cycling or the sinusoidal communication or degree of the overshoot that will be there, and how much time it requires to get to the final value, that is your control variable. That means what will be the time required for the obtaining the control variable, that is the settling time of the control variable. It does not give the character of the response for the different values of the gain of the controller. How its behavior will be, that is also not obtained by this Routh criteria. So, the second method, that is the root locus method, that is developed, which gives the degree of stability. It is basically a graphical method, a graphical technique for which the values of the roots of characteristic equation as one of the parameters, the gain of the controller is continuously changing. So you get or you plot a graph on which you are continuously changing the values of the gain and observing how this characteristic roots of this characteristic equation they vary with the different values of the controller gain. So by selecting the values of the gain, the controller, the characteristic equations can be obtained and the location of the roots can be plotted on the complex plane of different values for Kc. So roots they have been plotted. Again the same graph, the imaginary axis and the real axis. So the roots will follow even though they are having the negative values, the roots are having the negative values, the system is stable, but for the different values of the steady state gain, it is going to change or it is going to follow the different path for which it is going to transit from the stable region to the unstable region. If the values are 30 and above that, your stable system becomes unstable. So this detailed criteria or detailed analysis is not obtained by the Root criteria, and that is why the root locus diagram, which is a graphical representation, is came into the picture. So we are going to plot the different roots of characteristic equation and that root locus. Now what is basically a root locus? What is basically a locus? Locus is nothing but if the particle moves on a plane under a certain restrictions, it will be move along a certain path. That is, a particle, if I am throwing a ball and it takes a certain path, that is what the locus of the ball which is following the path, that is a parabolic locus that has been obtained. So this is what a locus is. Now the root locus, you require the characteristic equation, its roots, and how or what path they will take. So we have tried to plot a path for the different values of the steady state gain. So this is of our concern, what path that has been obtained, whether it is obtaining this path or it is obtaining this path. So that depends, or this knowledge of is obtained from the root locus diagram. It is a graphical representation of system, the transient response, and also the stability. It talks of the stability, it talks of the transient response, how it follows or which path it follows, that is obtained from this root locus diagram. It determines the actual values of the roots for different values of the gain Kc. It determines the actual values. What will be the value for the different values of Kc? So this path is nothing but the actual values what we plot. So it determines the actual values of the roots for different values of the gain Kc or the proportional sensitivity of a controller. Then the roots is a graphical representation of closed loop poles as a system parameter is varied. System parameter is nothing but your Kc. It can be used to describe the qualitatively the performance of a system as various parameters are changed. Then we can see the range of stability, instability, and the conditions that causes the system to break into oscillations. This is also can be understood by this root locus diagram. It talks of stability and instability. Not only that, it talks of the oscillations or the overshoots which are occurring in the oscillation process. It gives the transient response of the system subjected to a forcing function. So this root locus is nothing but a path of roots of characteristic equations traced out in the S-plane as system parameter varies from 0 to infinity. As the system parameter varies from 0 to infinity, whatever the path it takes. One way is to compute the roots of the characteristic equation for all possible values of the k, and computing the roots for all the values of k might be tedious for higher order system. So a graphical representation that comes into the picture in which the roots of the characteristic equation are plotted for all the values of system parameters. The construction of the root loci. How to construct this root locus diagram? The roots corresponding to a particular value of this parameter can then be located on the resulting graph. So you require the roots and what path they will follow depending on the values of the k, the graph that is to be plotted. By using the root locus method, the designer can predict the effects on the location of the closed loop poles of varying the gain values or adding the open loop poles and open loop zeros. So there is a need to understand what is the open loop pole, open loop zero, that we will study now. Now this is our general block diagram for any process. This is the transfer function of process, the transfer function of a controller, transfer function of a control valve, the disturbing factor, the measuring element that will be there. So writing the characteristic equation that is needed. So open loop transfer function is the product of all transfer functions in the control system when the feedback loop is disconnected from the comparator. When this feedback loop that is disconnected from the comparator, this feedback loop that is disconnected from the comparator and the product of all transfer functions in the control loop is the overall transfer function of the open loop control system. So open loop transfer function, that is nothing but product of all transfer functions in the control system when the feedback loop is disconnected from the comparator. So GOL is your open loop transfer function. So it incorporates all the different product of all the transfer functions. So characteristic equation of the control system, 1 plus GOL, 1 plus transfer function of the open loop system. Now this is written in terms of a general formula, the transfer function, which is equal to S minus certain values upon S minus certain values and the certain parameter. So determining the open loop poles and open loop zeros from the open loop transfer function. So it starts with the open loop transfer function. Open loop transfer function is nothing but the product of all transfer functions in the control system when the feedback loop is disconnected from the comparator. So open loop transfer function that is of concern, or that can be considered as the starting point for plotting the root locus diagram. So determining the open loop poles and open loop zeros. Now what are these open loop poles and what are these open loop zeros? The values of S for which the open loop transfer function becomes infinite is known as open loop poles, and the value of S for which the open loop transfer function becomes 0 is known as the open loop zero. And that is why all the numerator terms, they will be going to give you the 0, the value of S for which the open loop transfer function becomes 0 is known as the open loop 0. All the numerator terms that is going to give you the, for all the values of S for which the numerator values gives the value 0, that is considered to be as open loop 0. And if S something upon in the denominator, if it is 0, then your transfer function value that becomes infinite. So all the denominator values for the roots of this S, they becomes your poles. So open loop poles are indicated by the X and the open loop zeros are indicated by the 0. Then these are to be plotted on the complex plane. So the number of open loop zeros and are indicated by the A, and number of open loop poles are indicated by the B. Now in this equation there is only one open loop zero. So the zeros are indicated by the A. A will have the value of 1, and there are three open loop poles that will be there. So open loop poles, they are indicated by the B. So B will have the value of 3 and A will have the value of 1. So this is a generalized. Now you can write it in a generalized format. There are n number of the open loop zeros and m number of the open loop poles. Now coming to the numerical understanding. The certain transfer function, open loop transfer function, is given at gs, which is equal to k into s plus 2 upon s into bracket s plus 3. So for this, the s, which is equal to minus 2, that you will get the z1, that is your pole will have the value of minus 2. Similarly, for s, which is equal to the minus 3, the pole will have the value of P1 will have the value of minus 3. Then second transfer function Gs, which is equal to K s plus 1 upon s plus 2, s plus 3 and s plus 4. So in this case, s will be equals to the minus 1. So open loop 0 is minus 1 Z1. So A will have zeros are indicated by the A. So A will have the value of 1 and B will have the value of 3. And these values are minus 2, minus 3 and minus 4. So this is the open loop 0 and open loop pole. Now come to the block diagram. So R, Kc and the transfer function that is given for the process, and H is your feedback that is provided. We are assuming that the H is equals to the 1 unity feedback system. So the transfer function of the proportional controller is 1, is Kc. Then the open loop transfer function is given as the product of all transfer functions in the control loop, where H is having the value of 1. We are considering the unity feedback system. So the product of all transfer functions, that is Kc, into 1 upon s plus 1 and 0.5 s plus 1. That is what the open loop transfer function that will be there. Then you are having only the denominator value. Numerator, there is no value. So there is no open loop 0. A will have the value of 0. No open loop zeros. But there are two open loop poles for which you are getting the value of open loop transfer function as the infinity. S, if it is equal to the minus 1, then this factor becomes your 0. Anything upon 0, that is going to give you the value of infinity. So this open loop transfer function, if it is having the value of infinity, then you will get the open loop poles. So there will be the two open loop poles, that is P1 which is equal to minus 1 and P2 which is equal to minus 2. So the number of open loop poles that will be equals to B, which is equals to the 2. And A will have the value of 0. Then next block diagram. The controller is having the transfer function of Kc into 4s plus 1. However, the second or two non-interacting system, two interacting systems are there, that is 0.5 upon s plus 1 into 0.5 s plus 1 and h that is equal to 1 upon s. So I can write the open loop transfer function like this. The product of all transfer functions in the control loop, h which is equal to 1 upon s, this becomes 1 upon s, s plus 1, 0.5 s plus 1. So I can write in a generalized format, that is k into bracket s minus z1 upon s minus p1, s minus p2, s minus p3. So I will have the only one zero which is having the value of minus 0.21. S will be equals to the 0. S that can be equals to the minus 1 or S that can be equals to the minus 2. So I will have the values of three poles. So A will be 1 and B will have the values of 3. Next, the transfer function is given like this. So here also the open loop poles P1 equals to 0, P2 that is equal to minus 1 and P3 that is equal to minus 0.5. The number of open loop poles are B which is equal to the 3. The open loop 0 that is Z1 which is equal to minus 2. So A will be having the value of 1 and B will be having the value of 3. So we are doing B minus A which is equals to the 2. That is the asymptotic lines. How many number of asymptotic lines that will be there. So root begins at the open loop poles and ends at open loop 0. B minus A branches terminate at infinity. These branches follow the asymptotic lines. For the ith order poles, the I number of branches emerges from the pole. For jth order zeros, the j number of branches terminate at 0. The sum of the real poles and real zeros is the odd number. Then the real axis is the part of root locus diagram. The number of asymptotic lines are B minus A emerge from the center of gravity of the open loop pole and open loop 0.